In this unit, we're going to be talking about force, which is the cause of motion. And so dynamics compares to kinematics, whereas kinematics is looking at the study of motion, and then dynamics is the cause of motion. So the first visual that we're going to look at is an object at rest will stay at rest until acted upon by a net force. So let's say we had a hockey puck that's just sitting on ice, and yeah, as long as that ice stays cold and the surface stays flat, the object will stay at rest. And so this part of Newton's first law is pretty intuitive. It's the second part that's a little bit more challenging. So this is the second part. An object will stay in motion at a constant velocity unless acted upon by a net external force. So the example I like to give is a little bit goofy, but I think it's helpful. So here's Nice. And let's say we carved through the earth and we had a perfectly flat surface. Let's say here is Daytona, and then Key West way down here. And let's say we had our hockey puck, and let's say we had a vacuum chamber, so there's no air resistance. And let's say we had a perfectly flat surface with no friction. And let's say we got this hockey puck going, and let's say the velocity of the hockey puck was, let's say, like 3 meters per second. So along this whole way, as long as there is no net force, it's just going to keep going at 3 meters per second. We do have two forces. We have the force of gravity, and we have the normal force, which we'll talk about further later. But those two are balanced, so the normal force and the force of gravity are balanced out. And so, yep, it's just going to continue with the constant velocity as long as there's no net force. And this is the part that was misunderstood for really long until Galileo came along 2,000 years after Aristotle to fix this misconception. And so Newton was a huge part of fixing a lot of misconceptions. He was born the year Galileo died, 1643, and made a huge impact in how we understand the world around us. Just like Galileo, he helped clear up a lot of misunderstandings and really applied a lot of mathematics to what we understand now. And yeah, his findings and ideas paved the way for us to really understand the world around us. And he was born, like I said, the same year Galileo died. He was a really a genius in terms of understanding the world and mathematics and in science. Came up with the 3 laws of motion that we're going to be talking about, and invented calculus while he was still in his 20s to be able to solve things that we never could solve before, and so we're very indebted to what he's done. And he published the Mathematical Principles of Natural Philosophy, one of the most famous publications in all of science that outlines a lot of the ideas that we'll be talking about throughout the whole semester. So what is a force? Force is simply just a push or pull on an object. And forces cause objects to accelerate. So there are 3 ways objects can accelerate with forces. Things can speed up, things can slow down, or we can turn things. And so forces will do those things. So the first law, you basically just wrote down there with those 2 parts. The body in motion will stay in motion at a constant velocity, and the body at rest will stay at rest unless acted upon by net external force. And this is also called the law of inertia. So if there is no net force, then an object can't accelerate, and so it has to move at a constant velocity at that point. So just like that hockey puck that's continuing on there, it can't turn, it can't speed up, can't slow down, unless there is a net force on that object. One of the tools that we use to look at forces are what are called free body diagrams. So they're simple diagrams that show all the forces acting on an object, and only those forces acting on that object. So if we have a book resting on a table like this, we can outline the forces that are involved. We have the force of gravity, which is pulling down on the book. And then we have the normal force, which is pushing up on the book. So the normal force the word normal means perpendicular. So what is it perpendicular to? It's perpendicular to the surface. So the normal force is perpendicular to the surface, right angle here with the normal force and the surface. And so this is a very common force that we'll see all the time. Anything that's resting on a surface, it's balanced out by the force of gravity. Therefore, there are forces acting, but they're balanced. And so with that balance, there's no net force, therefore there's no acceleration. And then the sum of the forces, sigma, this is the Greek letter sigma, which is the sum of, or the net force equals 0, therefore there's no acceleration. And so we just did this where we have the free body diagram for a book, normal force of gravity, and if you notice with the picture, you can just draw a simple box for the most part. And so the first one I want you to try, and you can pause the video, is draw a free body diagram of a monkey hanging by its tail. Now go ahead and draw a box for the free body diagram, and then draw the forces from there. And so the simpler the picture, usually actually the more helpful it's going to be. So monkey hanging by its tail, so go ahead and try that, and then you can resume the video. Okay, so you should have drawn an upward force. This would represent the force of the monkey's tail. The tension force, Ft, is something that we'll use if we have ropes or chains in tension. And then we'll be discussing that more in detail later. And then we have the force of gravity. And so we know those are balanced. So if the monkey is not accelerating, those forces are balanced there. Okay, so the second part, you can try this as well. So you can pause the video. Monkey hangs from two vines, and the monkey's arms are at a 45-degree angle. So you can try that and then resume the video. Okay, so you should have drawn force of gravity here, and then force of tension going this way, or you could set a force of the monkey's arm or a force of tension, either way, going this way, equal there. And so now this one's a little bit different because we have forces going this way, force in the x this way, force in the x this way, force in the y, force in the y. So if we broke down the force of the monkey's arms, those two x forces are canceling each other out. This one's to the negative, this one's to the positive, and then these two that are going up would add together as a positive.